Hello, you. This is the podcast of Inside Science from BBC Radio 4, first broadcast on the 19th of January 2017. I'm Adam Rutherford. Radio 4 is currently bulging with science. Monkey Cage is back with a vengeance. Science Stories are on with a vengeance. And Jim El-Khalili is back with a vengeance on the Life Scientific. Inside Science is, of course, on every week, so no vengeance required. I don't really know what vengeance means. Anyway, here we go. If you've got a January cold and are currently trying to expel various viruses, we talk to the people who want to put viruses into you, and with good reason, their mission to search and destroy cancer cells. And mice are not men or women, but we use them all the time to understand disease and develop therapies. So we're taking a look at animal research and the validity of using mice and rats as models for us. And we say goodbye to the last man on the moon.
Houston, I can even see Poppy right where we're going to set this baby down. Man, Gordo, this is absolutely spectacular.
Apollo astronaut Eugene Cernan, who died on Monday. But first, news in this week that the British Antarctic Survey is to pull all staff out of its Halley 6 base in March for safety reasons. The Halley base is a fabulous piece of space-age looking tech, living quarters and laboratories all arranged to look like a giant caterpillar, and it's positioned on the Brunt ice shelf, which is floating on the Weddell Sea in Antarctica. There, British polar researchers and their colleagues make observations and run experiments that look at everything from space weather to global warming. So the announcement that they're all being evacuated is quite a big deal. Hilmar Gudmundsson is a geologist from the British Antarctic Survey, and he's on the line from Cambridge. Hilmar, tell us exactly where Halley 6 is.
Halley is located on the Brunt ice shelf, and maybe the first thing we have to sort of realize is this is a floating ice shelf. It's attached to the ice sheet, so it's not an iceberg, and the ice constantly flows, and an ice shelf like the Brunt ice shelf and all other ice shelves, they tend to grow in size with time. And eventually there will be a calving event, that's what we call it. There's a formation of big icebergs that break away. And currently on Brunt ice shelf, it looks as if such a calving event is in preparation. We have two cracks. One is called Chasm 1. The other one has now been given a name. It's called the Halloween crack. There's a more recent feature. We sort of saw the full extent of the Halloween crack in a satellite image from 31st of October 2016. So that was Halloween, hence the name.
If you didn't move Halley 6, which I know is on skis and can move with relative ease, if you didn't move it, would it float away on the newly formed berg?
So Halloween crack is not affecting the station directly. The other crack, Chasm 1, could have, because Chasm 1 was upstream, or is upstream of the Halley 6 research station. And for that reason, we relocated the research station, and that work is now pretty much done, has been happening over the last few weeks. So now the Halley research station is no longer downstream of Chasm 1, it's upstream of Chasm 1. So even if Chasm 1 were to grow and we were to have a calving event in that area, the research station would not be affected. It would not be floating on an iceberg. It would be safe on the upstream side of the Chasm 1.
And how are these decisions taken about, removing all the people from it, moving Halley 6?
It's a difficult decision. You have to balance things. But first of all, safety is always number one. So it's always the safety that is a top concern, safety for the people. Right now, there is no danger to anyone. The thing is, or what we're a bit worried about, is that if the situation were to change in the coming winter, which is south over here in this hemisphere, then our options of reacting to an evolving situation might be somewhat limited. So in summer, it's fairly easy to get in and out. There are airplanes, there are ships. In winter, the situation is very, very different. It's extremely difficult to get in and out. And for that reason, just to be on the safe side, we have decided that no one is wintering at the station.
Which seems sensible, and of course safety is the main priority, but this is Halley 6 is a very active research station. There is a lot of science going on down there through the summer and the winter. So what happens to the experiments that are running once everyone is evacuated?
Well, this is something that we are going through at the moment, really. We're coming up with plans how to minimize the impact, or negative impact on science. There will be some breach of the data missing the coming winter. There is nothing we can do about that, but we'll try to minimize this to keep the instruments going as long as possible and get them then started again the following season as early as possible. And some of these things can be automated. Some of them can be running throughout the winter, although they may not be transmitting data back. So we do whatever we can to minimize the impact on science.
And is there any indication that the growing, Chasm 1 and the Halloween crack, can you say in any way that they are related to global warming, or that the rate at which Antarctic ice shelves are melting?
This is almost definitely not related to global warming. An event of this is bound to happen eventually. It's just one of those things that ice shelves do. They grow in size and eventually a chunk breaks off. And this is a part of their natural life cycle. So this would always happen. Having said that, there are other ice shelves, particularly those on the Antarctic Peninsula, where we have seen a systematic change over the years, over the decades, where one by one ice shelves have disappeared, collapsed. And there the situation is clearly different. The ice shelves are not in balance. They are losing much more ice than they are gaining. And that is most likely due to warming oceans and warming atmosphere.
Hilmar Gudmundsson from the British Antarctic Survey. It's -3 degrees out there right now, and it's not much warmer here. And it's quite possible that you're nursing a cold, or worse, the flu. Most of the symptoms are your body trying to expel the viruses causing all that trouble. Now, Len Seymour is a researcher from Oxford University, and he's a man who wants to give people a virus. The idea is that seeing as viruses attack specific cell types, if they can be engineered to only attack carcinoma cells, then they could be a vital tool in the armoury against a whole range of cancers. And that's exactly what Len's team has done. Now they're in clinical trials for this so-called virotherapy, and I asked him how a virus can attack a cancer cell and leave healthy cells well alone.
When the virus gets into a cell, if it's a normal cell, nothing much happens because the virus can't replicate. But when it's in a cancer cell, then it starts to replicate its genome, it makes more DNA, and then it makes more protein, and then it kills the cell as it spreads to infect adjacent cells.
That is incredibly targeted. Just go through how it knows which one is a cancer cell and which one is a normal cell.
Well, there are several different features of what we call the cancer phenotype. So it's the environment of the cell, which is very good for the virus. So, for example, the inability of the cell to die is good for the virus. The fact that there's a lot of synthesis going on, and the fact that the immune system, particularly the interferon systems inside cancer cells, are very often deficient. So the virus is selectively able to proliferate within cancer cells and cannot do it within normal cells.
So what stage are you at in terms of turning this into a real treatment?
Well, the great thing about the virus is that you can modify it further to express biologics from within the virus, and that gives you a strategy for targeted drug production. Now, I say targeted production because it's different from targeted drug delivery in the sense that you don't have any of the active agent during the delivery step. It's only made when the virus gets to the target cell and then starts to convert the DNA into the therapeutic protein that you've encoded within the virus. We can arm it now to express particular biologicals selectively inside the tumour cells and secrete them into the tumour environment. And that provides tremendous potential for immunotherapy or for targeted biological therapies of different sorts. We can express antibodies from within it. Really, it's quite exciting for a scientist to think that you can express virtually any biologic selectively within disseminated tumours. So where we are with this virus is that recently we've shown that the virus causes, when it kills cells, a very pro-inflammatory effect because of the way it kills the cancer cells. And we're now starting to combine the virus with agents that will allow the immune system to be more active in people with cancer.
So, in a sense, if you're trying to develop it as a vaccine, does this almost work like a prophylactic, that you could actually prevent cancer from taking hold in the first place?
I wish it did, but the nature of the virus means that it will only replicate in cancer cells, so you can't actually use it in somebody who doesn't have cancer. So it has to be a therapeutic vaccine. It can't be as far as I'm aware, it can't use it as a prophylactic vaccine, although, to be honest, we've never tried.
But it could be used at a very early stage, though. So as soon as cells were beginning to, the primary tumour was beginning to grow, this is a stage where it might be very effective.
Indeed, I think that's the perfect situation for testing this virus, but also for testing a range of different agents, particularly if you imagine when a tumour is being resected, apparently curatively, but with the possibility that there may be some other cells around the body, then you want treatments such as this, which can pick up disseminated tumour cells before they become developing tumours.
So what happens next?
Well, this agent has been developed in laboratories, largely funded by Cancer Research UK. And when it became obvious that it did have clinical potential, Cancer Research UK and we worked together to start a spin-out company, and the company is now taking it forward into clinical trials. So far, we know one wonderful thing, which is that the virus can be given intravenously to patients and is capable of circulating around the body and infecting disseminated tumour cells. So we're very pleased, and as far as I know, this is the first virus worldwide where this has been shown to be possible. Now we're expanding on the early phase trials, which we call phase 1 trials, and we're also starting phase 2 trials, which are in a different subset of people. They're people who have cancer at an earlier stage, where there is every opportunity to do some clinical benefit, to achieve some clinical benefit.
So you're quite a long way down the road. It sounds like it's not going to be that long before this might be an available therapeutic.
Well, these are very rapid roads. In the last few years, things have been going incredibly quickly in the field of molecular oncology and the application of genetic medicines, particularly viruses. In fact, the very first agent was licensed to Amgen last year. That was also a British invention. It came out of Biovex, which was a UCL spin-out company. That agent is licensed for melanoma and has to be given locally, whereas the agent we're developing is designed to be given intravenously to treat disseminated disease.
So the virus, whose name I'm not going to attempt to pronounce because it has many syllables, you can do that, it targets specific cancer cells, but what types of cancers is it most appropriate for?
Well, we produced the virus to target colorectal cancer cells, but when we explored its activity, we found it's quite good on a range of different cells, cancer cells derived, for example, from the lung, from kidney, from breast, from bladder, essentially a range of tumour types that we call carcinomas, and they can come from many different tissues. So we're now trialling it against people with a range of different carcinoma tumours.
And the name?
Enadenotusirev.
Do it again.
Enadenotusirev.
Enadenotusirev.
That's it. You got it.
Yeah.
Well done.
Not that difficult after all. Len Seymour from the University of Oxford. Now, that virus is being tested now in people, but as with effectively every medical therapy, it's based on foundations of experiments that involve animals. In fact, pretty much all biology is heavily dependent on historical and contemporary data from animal studies. We often talk about mouse or rat models of diseases, and listener David Broadwood wrote to us questioning the legitimacy of these animal analogues.
What on earth is the point of using mice to study man? Mice do not get Parkinson's, nor dementia, nor cystic fibrosis, nor multiple sclerosis, nor depression, nor any number of a multitude of human diseases that they are being used as models for. Doesn't that tell you something?
Now, we thought this was a valid question, and it was prompted by a discussion recently on Inside Science about new advances in understanding how Parkinson's disease develops. Patrick Lewis is a Parkinson's researcher at the University of Reading, and I asked him if David's concern is justified.
I think he raises a very important point. There are some big differences, and it's kind of stating the obvious. There are big differences between mice and humans. And so when we try and model really quite complicated neurological disorders in a mouse, it can be quite difficult to extrapolate from results that we get in a mouse model to what happens in a human. And that means that drug treatments that we develop based upon a mouse model can be difficult to translate into humans. And actually, we have a very good example of this with Alzheimer's disease, where mouse models generated from human data, so human genetic data implicating a particular gene, a gene called APP, generated a system where we could test whether or not altering the levels of this gene or the protein that comes from it make a difference in terms of Alzheimer's pathology. And a lot of academics, a lot of drug companies became very good at removing some of that extra protein, a protein called amyloid beta. So we were able to remove that from the mice, and that then allowed pharmaceutical companies to start testing this approach in humans. And to date, none of those approaches have worked in human trials. So it's raising a very valid point, and I think, to my mind, the most important thing is to be critical of data that comes from animal models. And this is true of mouse models, but it's also true of other animal systems as well.
So when we're talking about the differences, as you say, it's obvious that there are differences between mice brains or rat brains and human brains, and it's not just size and it's not just structure. But I think with regards to neurodegenerative diseases, one of the key issues is that mice don't get Parkinson's. They don't get a disease which is like Parkinson's. So how does the model even work?
So I think it's important to remember that what the animal models allow us to do is they allow us to look at very, very specific questions in a relatively controlled environment. So, for example, the gene that I work on, a gene called LRRK2, which is very important for Parkinson's disease, we know that if you have a mutation in that in humans, it causes you to develop Parkinson's. And the mouse models allow us to manipulate that gene, see what happens when it's removed, see what happens when we insert the mutations, and look at the consequences, not just in the whole animal, but also in individual cells. So it allows us to look at mechanistic details of what a particular pathway, a particular gene is involved in.
So what do you do? Do you mutate the gene, the equivalent gene in mice, and does it produce a version of mouse Parkinson's?
So that's very much the strategy that a lot of groups have taken, inserting mutations into a mouse or into a rat and seeing what the consequences are. And actually, for Parkinson's, the results have been very disappointing in terms of generating a disease which looks like human Parkinson's. Mice who have mutations in pretty much all of the genes that are linked to Parkinson's do not develop something that we would recognise as Parkinson's disease.
So David Broadwood wrote in, and is he right to assert that mouse models of Parkinson's are of no value? I mean, you've just said that they don't develop the same symptoms even when you induce the same mutation that we see in humans.
I think taken in isolation, data from mouse models doesn't allow us to immediately make a massive leap that allows us to develop a new treatment for Parkinson's. And again, to my mind, I think the important thing here is to remember that they're part almost of a sort of hierarchy of information. My own work focuses on looking at what a particular gene and protein does in a cell or in isolation, looking at the biochemistry of that protein. If you add information from that to information that you get in more complex organisms, so moving through to zebrafish or to the fruit fly or to nematode worms, you can start building up a picture of what this gene does in each of those systems, in each of the nervous systems of these organisms. And mouse models are a very important part of that because they allow us to look at a more complex mammalian system. Now, they may not get Parkinson's, but they do provide us with insights. And that's certainly true of mouse models of Parkinson's. They have allowed us to look in different directions that we wouldn't have gone to had it not been for mouse models being generated.
One of the phrases that a climate scientist used in an interview on this programme when we were talking about models and modelling complex systems such as the climate is that all models are wrong, but some of them are useful. Now, does that work for neurodegenerative diseases and using animal models?
I think that's a very, very good way to describe it because you are never going to get the full picture of a neurological disease that afflicts a human in a mouse. So from that point of view, the animal model will be wrong, but you can take important and useful information from that model.
Patrick Lewis from Reading University. As ever, do write in with your thoughts on this or any other topic. The email address is bbcinsidescience@bbc.co.uk. Now, it's a blustery January outside the studio, and even though you don't need a weatherman to know which way the wind blows, it turns out that we know very little about wind speed and wind direction, and this is one of the reasons that predicting the weather is tricky. Well, the European Space Agency and Airbus have been working together to make Aeolus, the first satellite specifically designed to measure the wind using a laser surveying technique called LiDAR, and it's being launched later this year. We sent Caroline Steele to visit Aeolus at its home in Airbus Stevenage.
Right, so I'm just robing up. I'm putting on. That's me getting ready to see Aeolus, the wind-detecting satellite. It's been built in Stevenage over the last 15 years, and this was my last chance to see it before it heads off for its launch later this year.
Why has legs? Why does yours not have legs?
I'm Richard Wimmer, the Aeolus project manager here at Airbus Defence and Space Stevenage.
But as we're already able to monitor the wind, why do we need this satellite?
Wind data is collected at the moment from a number of sources, aircraft flying above us all the time and recording wind speed. There's various sounding balloons that are launched up through the atmosphere to measure wind speed. But it's all collected at discrete points or on routes where aircraft regularly fly. But there's nothing at all collected on a global basis. So there's nothing over the Atlantic Oceans, over the Pacific Oceans, over the tropics, where many of the weather storms that formulate and even impact us here in Europe start their life as storms in the tropics.
We need something which can give us more detailed information over a larger area. How can Aeolus provide this?
I'm Professor John Remedios. I'm Director of the National Centre for Earth Observation based at the University of Leicester. What this satellite does, it has a sophisticated laser instrument. It sends out a beam into the atmosphere, and essentially you need the atmosphere to return a signal to the satellite, and that occurs through scattering by molecules and also by clouds. The molecules in the air and the clouds are, of course, moving with the wind, and that motion actually causes a shift in the frequency of the return signal. So the laser sends out a signal at one frequency and you get it back at a slightly different frequency.
How will this data impact us here in the UK?
What it will aim to do is improve the accuracy of the forecasting. So they expect to be able to predict with accuracy an extra day in advance every 10 years. Normally we can predict fairly reliably today about 3 or 4 days in advance, and every 10 years they expect that to increase by 1 day.
And this satellite would actually give you a better insight into changes in circulation that we don't often talk about as a result of climate change. We recognise that maybe it will get stormy, maybe it will be fewer storms in a particular region like the UK, but actually we want to know better than that. We want to be able to observe signs of that change, and I think this mission will help with that.
There is no doubt that Aeolus will be having a big impact, but there were challenges along the way. In fact, it was due to be launched in 2007. So what went wrong?
When you take them to space, you take them to a vacuum, and suddenly your laser starts to do different things. It may not be as stable, and in particular, one of the effects was that the components, the optical components through which the laser beam passes, they have to have coatings, and those coatings deteriorated with time in the vacuum. So what the industrial team had to do was to actually face a new problem. How do these laser beams work in optics in a vacuum? And can we design new coatings that will allow the lasers to maintain a focus beam, but also to last for a long time, because actually there was a problem with the return of signal in the lasers.
We've had to develop the technology as we've gone. And in fact, in some instances, we're on about the 3rd generation of coating technology since the start of the project.
Richard and Airbus account manager Ralph Cord kindly agreed to take me to see Aeolus in its special clean room. But as you heard earlier, in order to protect the satellite, I had to put on a big white suit. I'm putting on a large white onesie that I'm hoping is going to fit, that I don't step through with my boot. Oof.
And now you need to put the overshoes on. And then finally you need to put a hair cover on with...
It's going to be a great look. There you go, am I in?
It consists mainly of 2 main sections. One is a big, shiny box section, which is the satellite bus, which contains all the equipment for guiding and controlling the satellite. And then on top, we've got in a cylindrical white shroud, a telescope and an instrument at the heart of it. And that's what Aeolus is all about. It's about a laser embedded at the heart there.
If I were to run up to the satellite and sort of dump some hairs on it, what would happen if we still launched it covered in my hair?
Well, first of all, I'd try and stop you. But things like that are a danger to mechanisms on board the satellite and to the optics itself. We don't like in a camera that we use to have a bit of hair sort of on the lens. It's even worse when you're doing something where the quality of the data is very much tied up with the quality and the precision of the optics and the performance of the laser. So it's absolutely at the limits of its capabilities to do the mission it's going to do, so we don't want anything to interfere with it.
It was amazing to see the satellite before it leaves the UK on its journey to the launch pad.
It's a funny time. I've been looking forward to seeing it completed for quite a few years, so that was an exciting point, to actually see this complete spacecraft in our clean room. Now, to wave goodbye to it, I know it's important, it's a bit sad to do that, but it's on its final journey, and we can then be seeing it launched from Kourou in South America, hopefully later this year.
The exciting moment will be in that first laser pulse goes out into the atmosphere and comes back to the instrument. That is the moment when you see that signal. That will be incredible.
John Remedios ending that report from Inside Science's Caroline Steele. Finally this week, and then there were 6. Starting with Neil Armstrong's giant leap, 12 men walked on the moon in the Apollo missions. On Monday this week, Eugene Cernan, the last person to stand on the lunar surface, died at the age of 82. Cernan was commander of Apollo 17, which blasted off from the moon on December the 14th, 1972. Cernan and geologist Harrison Jack Schmitt had arrived 3 days earlier and spent in total more than 21 hours on the surface. This was his reaction on the first step outside.
Jack, I'm out here. Oh, my golly. Unbelievable. Unbelievable, but is it bright in the sun?
Gene Cernan was someone who began to dispel the image of astronauts being very straight arrows. Being cool-headed and ruthlessly reliable is how you want an astronaut, but Cernan clearly also liked to have a laugh, and he was a bit more relaxed on the surface of another celestial body than some of the previous lunar men. Nowadays, we're a bit more used to astronauts like Chris Hadfield singing Bowie on the International Space Station, but Cernan was singing in space more than 40 years earlier.
I was strolling on the moon one day in a merry, merry month of December. No, May's the month. May, that's right. May is the year of the month. When, much to my surprise, a pair of bunny eyes. Sorry about that, guys.
Cernan had a reputation for being a bit reckless for an astronaut. He crashed a helicopter in the Atlantic whilst chasing a dolphin and reportedly slid down a banister at the White House. Nevertheless, space is hard, and even though the public had grown accustomed to what remains an extremely hazardous endeavour, Apollo 17 was a technical and scientific success. Cernan and Schmitt retrieved 111 kilograms of moon rock and brought it back home. They set up dozens of experiments and even took with them 5 mice for observations on exposure to cosmic rays. Cernan nicknamed them Fee, Fi, Fo, Fum and Fooey. The scientific legacy of the Apollo missions cannot be understated. We know the age of the Earth because of those moon rocks, and with over 2 tons of scientific equipment deployed to the surface and more than 2,500 scientific papers citing Apollo data, much of the basis of planetary science was laid in those 4 missions. This is Inside Science from BBC Radio 4, and we sign off with the words of Eugene Cernan, Apollo astronaut who died this week. His real legacy should be that he is not the last person to walk on the moon.
And as we leave the moon in Taurus Littrow, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind. Godspeed the crew of Apollo 17.